Welcome to the video Isotherming, Austempering, the ausferritic reaction. You have seen that we described three patented materials. IDI, C.A and ADI wear. There is many discussions why these materials are patented and why patent application have been done and this patent has been granted. The main reason is not for making profits by royalties. The main reason is to protect the right technology. Heat treatment of spheroid graphite cast irons is not an easy matter. It is a complicated matter that takes in account chemistry, nodule count, segregations, heat treatment, robust plants to do castings and to do heat treatment. These materials up to now are not developed as their potential can indicate, because the potential for substituting steel application is very large. And the question is why we are not producing million and million tons in the world. And now we try to explain why. And why the first development of ADI has been, for instance, protected by the Germanite process, the Dr. Miberger license that we get in 85, and why now we have these two patent IDI and ADI were protecting these two new materials. The intention is not to be the only one producing this material. We are willing that many good professionals are doing and are promoting and are producing this kind of material. But from the experience of ADI, we know that everything has to be run in the right and proper way, with the right and proper knowledge, with the right and proper people, with the right and proper plants. Otherwise, especially for ADI, we have a problem of austenite stability, we have problems of bad machinability, and we can create also bad reputation, not to a single process, but to the material itself. That is an obstacle for a great and professional diffusion. And we see why. So when we have the change from the austenite temperature to the salt bath temperature, and we start the ausferritic reaction, we know that the ausferritic reaction starts from the first to freeze, from the nodule, and progresses to the grain boundary, to the last to freeze. And during this process, the austenite content decreases, ferrite is increasing, and the residual austenite becomes stable and more stable, until to reach an equilibrium where the ausferritic reaction does not proceed anymore. But the time needed to do this, to complete this reaction, depends on the distance between two nodules and depends on the pattern segregation we have. That in turn depends on the alloying elements we selected and how they did segregate at the solidification time. This is described through the so-called Dorazil curve. That is describing the amount of the phases in during this reaction. You see that in yellow, I evidenced the so-called process window. This time, this level of the phases corresponds to the maximum stability of the austenite. That means the better machinability. That means the better impact strength, impact energy to be absorbed. That means the best fatigue properties when you have notches or cracks. This process window, the yellow time, can be minutes or can be hours. It depends from the segregation pattern, but it also depends from the heat treatment parameters. And you can understand how this process window is different in a thin wall or in a large wall, because the nodule distance is different. And also you know that castings are the best process to obtain complicated shapes where you can have thin and thick sections in the same casting. So if we want to use the casting process, we need to face with the differences between different casting sizes that are processing with the same austempering batch, the same austempering process. So to do this, we need to have this process window as large as possible, because if the process window is narrow, we can have that the thinnest section completed the reaction while the largest section didn't arrive to the austenite stability. And if we leave time for the largest section to reach the austenite stability, the thinnest section can pass from the so-called stage 1 to the so-called stage 2, where the supersaturated austenite converts itself into carbides that are more dangerous, even more dangerous than unstable austenite. So we are obliged to get a large process window if we want to have good ADI castings that are machinable after heat treatment. Otherwise, it happens like you see in the micrograph, where you see the white region that is the last to freeze, the grain boundary, unstable austenite that at room temperature is transformed into martensite. We have seen why it happens, because of segregation. Then, what does this segregation do? You see, this is the ferrocarbon ion-carbon diagram, where at the eutectoid temperature, where you see the austenite carbon, the carbon solubility into austenite, that is the obliquous line on the right. And then you see the obliquous line on also on the right, but on the bottom. That is the carbon solubility into the metastable austenites after the reaction. So what these elements are doing, the addition elements, copper, nickel, and moly, and manganese, the addition of these elements is changing, is displaying, displacing the carbon solubility into austenite. And the effect of manganese, for instance, is to increase the carbon solubility in the primary austenite on the top, but decreasing the carbon solubility into the metastable austenite in the bottom. So there is a rule. The rule is that the reaction rate, ausferritic reaction rate, depends on the so-called driving force. What is the driving force? The driving force is the difference between the carbon content into the metastable austenite and the carbon content into the primary austenite. So you see that in the first two freeze, where we have high silicon and low manganese, we see that the carbon content into the primary austenite and in the metastable austenite is represented by the red flags, red arrows, sorry. And so, while in the last two freeze, in the grain boundary, it is represented the carbon content of a primary and metastable austenite is represented by the blue arrows. You see how the difference in the driving force is much higher in the first two freeze than in the last two freeze. So the first two freeze is represented by a Ferrari car that is very high-speed car, while in the last two freeze it is represented by an old tired man that is reacting very slowly. And so this is the reason why the manage of the process need to be very professional, knowing what we are doing and the influence of every parameter. But you see that we have the austempering temperature, the low horizontal line is fixed, and it is depending on the gray we wanted to achieve, the strength or the hardness we want to achieve. This is given. In addition to the segregation pattern that is moving the carbon solubility into the primary and the metastable austenites, we have another parameter that we have to choose. This is the austenitizing temperature. The austempering temperature is fixed. It depends on the grade. But we can move the austenitizing temperature. We are free to do that. You see that if we increase the austenitizing temperature, the carbon solubility into the austenite increases. Then the driving force decreases, both in the first to freeze and also in the last to freeze. And decreasing the driving force, the reaction is slower. The austempering time, the austempering reaction takes more time. More does not mean more minutes, means many more hours. So, if the combination of the carbon solubility into the austenite, primary and metastable, and induced by segregations, and the austenitizing time, if this combination is not proper, we risk to have a bad process window, as we have seen before. And we need to avoid this.